Hey, AP Chemsters, this is Mrs. Vanderwall bringing you another edition of the Blank Wall series. This is the last one for chapter 13. So this is all about catalysts. And if you recall that video that we saw with the boy and the girl running the hallway and colliding and books are flying, there were 5 things that could make a reaction go faster. And catalysts are talking about the 5th thing. A catalyst is a substance that will speed up the reaction. The definition is that it speeds up the reaction without it being consumed. And this is the other key point about what a catalyst is. It will lower the activation energy, but does not change. Cross out that DE. It's supposed to be a delta, a triangle, delta E, so it doesn't change the overall energy for the reaction. Catalysts will provide alternate reaction pathways. And finally, catalysts result in higher percentage of effective collisions. And that is where that idea of the matchmaker came in from that prior video. If you remember, the matchmaker would orient those students so that they could gaze into each other's eyes and fall in love, and they didn't have to go running in the hallway and colliding to do so. So the reason why catalysts result in a higher percentage of effective collisions is that the catalysts themselves will help orient the reactant molecules so that they will have a higher percentage of effective collisions, so that the right things will collide with each other and make it a whole lot easier for that reaction to occur. And therefore it will actually lower that activation energy, so it doesn't take quite so much energy. Those students don't have to run the hallways now to do that. So there are 2 different kinds of catalysts. One's a heterogeneous catalyst. It's very important in industry. They use this a lot. It's usually a gaseous reactants on a solid surface. Platinum and nickel are good examples of heterogeneous catalysts, and they provide a surface for this reaction to occur. And so it provides a place for this correct orientation to occur. There are 4 steps to this, and you can read through those. You can see the uses, conversions of alkenes to alkanes, and maybe a little more important, a conversion of carbon monoxide and nitrogen monoxide in auto exhaust to create carbon dioxide and nitrogen gas. Another type of catalyst is called a homogeneous catalyst. And this is a really important one. This is where reactants and catalysts are in the same phase, typically all in the gas phase or maybe all in the liquid phase. A very important example of this would be the decomposition of ozone. And I don't know if you guys remember this. If you talk to your folks, they'll probably remember in the 80s and the 90s, there was a big deal about the ozone layer. The ozone layer was being destroyed, and they found this to be a link between the use of aerosols and the destruction of the ozone layer. And the key ingredient in the aerosols that caused this to happen was called CFCs, or chlorofluorocarbons. Freon, if you look at the formula, is an example of a chlorofluorocarbon. And what happens if these aerosols are putting these freons into the atmosphere? Now they are very available for light to reach them, and they're in the atmosphere, and the light will actually decompose and pull off a chlorine. And now this chlorine is what's called a free radical. And this is what is the danger to the ozone. So the freon itself isn't, but the decomposition of the freon is what is dangerous to the ozone. So this chlorine right here will attack an ozone molecule, creating an intermediate, which is the ClO, and oxygen gas, which, well, hey, isn't it good to form oxygen gas? Well, not at the destruction of ozone. No, it's not. So then what? Well, this ClO then goes ahead and reacts with another oxygen molecule, oxygen atom, and creates an oxygen molecule and chlorine again. So note, the overall net reaction, like we learned in section 13.5, when you look at the overall reaction, the chlorine molecules cancel each other out. They're not part of the net reaction. As is the intermediate, the ClO, is also canceled. Remember when you talk about Hess's law, you can cancel them out, and this is our net reaction. So what's going on here? Well, if you notice that chlorine here is being used in step 1, but it's being regenerated in step 2. Go back and look at our original definition. It is a substance that speeds up the reaction without itself being consumed. And that's why it is so dangerous. Just a little bit of Freon can continually destroy the ozone. And if you know anything about ozone, it is what protects us from the UV radiation from the sun. So the aerosol, the Lysol spray or the hairspray, the chlorofluorocarbon in that aerosol, just a little bit of it in the atmosphere was doing great damage. So things have changed, rules have changed, and actually, if you come back to what's going on now, the ozone, they say, is repairing itself because of our awareness of the dangers of too much chlorofluorocarbons. All right, so again, letter C says, notice that chlorine gas is not used up anyway, which is a qualification for it to be catalytic because it is being created again in step 2. This is also why very small amounts of chlorofluorocarbons, again, CFC, such as Freon, can do immense damage to the ozone layer. So anyway, let's turn the page. Okay, so let's try problem number 32. It says, using the reaction coordinate diagram, answer the following questions. I'm hoping this diagram looks rather familiar for you. We've seen this before back in chapter 6, but we've added a few little twists to this, and so let's see what's going on here. What are the reactants? Well, hopefully you see right over here, X2 plus Y2, those are your reactants. We've seen that before. Your products, if you look, yes, they are right here. It says 2xy. So what is this right up here called? So that's x2, y2. Well, that is kind of like the interval between breaking bonds and forming new ones. We call this the activated complex. Activated complex. I'll just abbreviate it. Okay. So it's the activated complex. This is that place between, like I said, you're breaking some bonds, you're trying to form some new ones. So it's that in-between stage. So it says label the chart above on the activation energy and the overall change. Now, the activation energy, if you remember, is the energy required to get up over this hump. So you have to start from where the reactants are and work towards the top of the hump. So that would be, and let me abbreviate as EA here. That's your activation energy. And then it says label the overall change in energy. If you recall back in chapter 6, it was always products minus the reactants. So here's your products minus your reactants. So this would be your change in energy. Okay, we also called it delta H if you recall. So what is the value, including units, of the activation energy? Well, it's right up here. It's 130, and this looks like to be 50. So 130 minus 50 looks to be 80, and the units look to be kilojoules. So now what? What's the overall change in energy? If you recall, that is always, again, products minus reactants. So it is a positive 50 kilojoules. Now, what do you remember about it being positive? Hopefully, the idea that this is endothermic comes back. Now, this problem didn't ask you this question, but I'm going to ask you this question. What does adding a catalyst do? Well, we said in the first page, the page right before this, that a catalyst is going to lower the activation energy. So we're going to lower the activation energy. So I'm going to come to about like so. So now this is the new activation energy. Okay, and so if you were to actually do this, I don't know, does that look like to be about 115 to you? I'm just guessing there. So the new activation energy would be about 115 minus 50. That looks to be about 65. So we have actually lowered that activation energy. It is no longer 80 kilojoules. It is now 65 kilojoules. It's easier for those reactants to get over that hump. So to make that analogy again, the boy and that girl in the hallway, they don't have to run as fast to collide and throw their books up in the air and fall in love and go to the dance. So the activation energy has decreased. Now, hopefully this reaction coordinate looks familiar. Very, very similar to the last one, probably a little bit more common in a sense. Our reactants are right here, A, B plus C. Your products are A plus B, C. If you notice that B has separated from A and has joined up with C. So we broke a bond, we formed a new bond. ABC, once again, is that activated complex. I'll just write AC. And again, it's that transitions, that interval between your reactants and your products. So we're in the process of breaking bonds. We're in the process of forming new bonds. Again, label the chart above for the activation energy. So again, reactants up to the top. Here is your activation energy. And it says the overall change in energy. So again, that is products minus reactants. Notice we're going the other way. So what is the value of the activation energy? Well, it looks like 80 minus, I don't know, would you say that could be like 55 or something? So if we call that, so 80 minus 55, I hope I can do that math in my head. What is that, 25? So the activation energy looks to be about 25 kilojoules, I bet. Okay. And so now what is the overall change in energy? So it would be products, which I don't know. How about 18? I think that looks like an 18. What about you? Minus, well, again, let's call that 55. And if we're to do that, I believe that is negative 37. What was that? Negative 37? What does that negative tell me right here? That it's exothermic. And if you recall, yes, more reactions are probably exothermic than endothermic because it's more energy favorable to release energy than to overall gain energy. Once again, like I said, they didn't ask you this, but what would be the effect of adding a catalyst? It would be to lower that the activation energy. So if you notice, it has less of a hump to go up over. Let me just, we're done with the problems. Let me just kind of talk to you real quick about a very common catalyst, and that's maybe one you heard about in biology class, and that would be your enzymes. So if you're to take a breath, you had to have, I think I've read 22 chemical reactions had to occur for that air that you breathed in, the oxygen, to be converted into carbon dioxide. So in a very short moment, all those chemical reactions had to occur. How come they occurred so quickly? Is because you have catalysts in your body to make them occur quickly. Another very common enzyme in your body is actually in your saliva. So if you were to consume food, the first part of breaking down your food would be those enzymes in your mouth, in your saliva, to, let's say, break apart the starch, which is a polysaccharide, into the individual glucose pieces. And that's why starch will give you lots of energy. So you have an enzyme that is just for breaking that special bond to make all your glucoses, come off of the starch molecule. And how come that happens? That, again, that enzyme will directly affect the orientation of the starch molecule so that the key bonds will indeed break. So again, this is the idea of catalysts. Now, I have also put in Schoology a video by Bozeman. It says, I think, Bozeman Catalyst. And I highly recommend you go click on that because it has graphics that there's no way I could have that. It shows you this idea of orientation in a much better visual way than I certainly could using this format. So I would go ahead and look at that Bozeman video. It's about a 5-minute one, so it's not much more of your time. And that should conclude your idea of catalyst. I hope this was helpful. And again, if you have any questions, jot them down. And I know Mrs. Blankenship and I would be happy to answer them. Have a good night.